that like a new? Don't we have like a new place? Yeah. See the little one?
Yes. Well, they're all kind of little.
They are. Did you hear Mr. D said he was like, all right guys, get up here so that everyone can see you. And he's like, not that you guys are short or anything. It's really good.
All right, here we go. Here we go. So yesterday, we were told that the growth is exponential. Because, I mean, let's be honest. You were given 2 ordered pairs, right? Could you have written a line through those 2 ordered pairs? Yes. We didn't. We wrote an exponential function because they told us the growth was exponential. All right. When will the population surpass 1 million? So we had done this part. We had gotten our equation written. Look back at your notes. Confused by that. We've written our equation. Now I need to answer the question. When is the population going to be 1 million? Well, what will I do here in terms of my equation?
Do a line for y equals 1 million and see what the 2 equations are.
Okay, so we had talked about 2 ways to do it, and one way was to do it graphically. Okay? The other way,
Take the log of both sides.
the other way is to put 1 million in here, and this is the way I want to do today because we haven't done, I don't know if we've done any of this. We certainly haven't done much of it. So I want to solve this algebraically. So we're all clear we could solve it graphically, right? Put in this equation, put in 1 million, and look right across. That's an exponential, so you know its shape is going to be like this. Here's 1 million. That would be the point you would be looking for if we were doing it graphically. But we're going to do it algebraically. Lucy is exactly right. We're going to need logarithms to get that x. I mean, we can't solve for that x because there's no common base. It's not like on your quiz you took yesterday where you could change both sides into 2 to a power or 3 to a power or something. You can't do that. So we're going to need logarithms. What's step 1 now?
Divide.
You've got to divide. Please don't round off. Just leave the fraction. We're going to type it into our calculator soon enough. But you will discover that everything you round is going to cause your answer to be off more significantly than you might think. So we're going to divide by this initial value. Okay? Now, we're going to take the logarithm of both sides. And when we do that, the reason we do that, the beauty of it all, is that it will take that thing that was an exponent and it pulls it off and puts it out in front. Do you remember that? That when you take the logarithm of something to a power, the power becomes a coefficient. That is one of your main properties of logarithms, and it's the most beautiful. So now, since that x is now a coefficient, to get x by itself, now all we need to do is divide by this. So we're going to have the log of and you're going to divide it by the log of this. All right, so let's all type that in on our calculator, make sure we can. And then we have to talk about what our answer is going to be. What'd you get? I did not. Okay, wait.
Oh, wait, no. That's wrong.
Anybody get anything?
That's a question.
Okay. Anybody get this, get an answer?
No, 18.
That's what I got, I'm going with Lewis, that's what I got, 18.21. Alright, so I'll get any questions in a second, but let's finish this. Remember in the beginning when we set our problem up, remember, look at your notes. The ordered pairs I used were 0, comma, and 10, comma, right? Because I defined X as the number of years after 1990. So if the answer is 18, and it says, when will the population surpass, what are you gonna say?
In
2008? Sometime in 2008? Because we started counting in 1990. So sometime in 2000, early in 2008. Dom?
How do you do that on your calculator? Like, I know what the log button is, but what's like the order?
Okay, just, once you press the log button, these parentheses will come in automatically. And so you just do that, close the parentheses, divided by, log, and then again, another parentheses will come in, type in that number, close it, delete this, and it should come out. Lucy?
So when you were at first, when you did the 10th root to find the, what b equals, if you were to round b off, would you get a way different number? Like, instead of continuing it all the way out to
Yeah.
0.358.
Yep. Now, it's not gonna be way different, but it's gonna be significantly different. So, my suggestion to you is really in any problem, but certainly where exponentials and logarithms are involved, carry a bunch of decimal places. Now, I'm not saying you have to write out, all 15
Yeah.
of them or whatever, but carry a bunch.
Okay.
Till your final answer, then you round it off. And then ideally, we won't be rounding it all, going straight to the calculator. All right, who else had a hand up? Somebody else had a hand up.
Can you explain the part of like the log 1.01358? How like putting the log of that makes the exponent equal to
It's a property of logarithms. It's exactly like why 3 plus 4 is 4 plus 3. It's a property. So it's a truth, it's a fact. So we could go through and derive the properties, but I don't want to do that. We don't have time to do that. It's one of the laws of logarithms. Okay? And it's the one we use all the time. We use it all the time.
if it was like, let's say that instead of X, it was just like 2 or something, then would
Then
it
I
be,
wouldn't be using logarithms. I mean, I could. It would
yeah,
be
but
2 times log, but the whole reason I'm using logarithms is because there's no other way to find that exponent. You can't solve for that exponent algebraically
yeah,
unless you can get it down.
okay.
So if it's a 2, I'm not using logarithms,
Right.
I'm squaring, right? I'm only doing that when it's an X or some kind of
So
derivative.
if you do a logarithm to one side, you have to do the other side.
Huh?
If you do a logarithm to one side, you have to do it to the other side.
Yeah, it's an equation, right? Whatever we do to one side of the equation, we have to do to the other side. Yes. Please do not be doing things just to one side. All right, so now everybody's practiced. Did you all now get 18.21? Okay. All right. Let's look at, we're gonna do some more of these. Don't worry, we're gonna do some more. But let's look at the next one and see what it has to offer. All right, so based on recent census data, a logistic model for the population of the town is this. So later today, we're gonna be writing our own logistic functions, but somebody has already figured this one out. And I have to be careful, this little tiny writing is not good for my old eyes. And the 0 in front of the decimal point messes me up, so I think I got it.
That's yours, right?
That's 21, is that a decimal
Yeah.
point there? 0.602. All right, so here's the question. According to this model, when was the population 1 million? And I wanna do this algebraically. Again, we all know we can do it graphically. Type in that equation, type in 1 million, and look where they cross. We're gonna do this algebraically. So we want the population to be 1 million. So let's talk about how we're gonna solve this equation. Okay, so let's just think about that for a second. It's not hard, you can do it, you gotta be organized. It's kind of messy. Lucy?
Would you need to find the y-intercept?
What?
Would you need to find the y-intercept?
To solve the equation, I don't think so. I kind of think that that would have benefit, I don't know. I can't think of why I would do that.
Would you need to flip the 21 to negative exponent?
Okay, now be careful, because the 21 doesn't have
the
the
E.
exponent, only the E does. Could I write this as 1 over E to that power? I could, but that's gonna make it
If you put it in the
denominator.
calculator.
Yeah, since I'm doing it on the calculator, I really don't have a need to do that. Finley?
Probably just divide by the numerator to start.
Well, I can't really work all this out. I would like to work all this out, but I can't because of that, right? Lewis?
Just like multiply at the denominator.
Yeah, multiply it over to here, right? I gotta get that over to here. So I'm gonna have 1 million times, well, I'll just go ahead, that's gonna be 1 million plus, okay, now you're gonna have to help me with this. 1, 2, 3, 1, 2, 3. What was the original here? 1, 2. I think that's right.
2,160,000.
I got 21,602,000, is that right? If I take this times 1 million. I think that's right. So I brought, I'm not solving an equation, so I brought the denominator over here and took it times 1 million. Okay, now what do you think we should do? Subtract 1 million. And so is that gonna be, is that gonna be negative 301, or not negative, 301,642?
Just divide by 2.
Divide by the 221 million number now. So e to the negative 0.05054t equals whatever this is divided by that, and I'm not gonna type that in yet. I don't wanna round that off. I got plenty of time to type that in.
Now you do the log.
Do we take a natural log?
And now, okay, you can do either one. You can LOG if you want. LNing is more convenient, natural log, because E is the base of the natural logarithms. And when you have ln E next to each other, they're inverses and they cancel each other out. You remember that from last year? So in any problem, in any situation, if you have an ln and an E right next to each other, they will cancel each other out. So I'm gonna ln both sides. So Tess, I'm still lning both sides. But those are gonna cancel because E is the base of the logarithm. So this is like log base E of E, they cancel. So negative 0.05054t equals ln of that fraction. And then to get my answer, I'll have to do the natural logarithm of that fraction divided by the negative 0.05054. Does that make sense to you?
Wait, so
Where'd what come in? 1
from the original?
up to the left.
But one was just a million. And you just drew one.
Yeah, the one
The
fifty.
1 got multiplied over here, so it became a million. And then we subtracted the million.
No, when you
All right, so what's happening here? I'm getting ln 301 642 divided by 216 divided by negative 0.05054. Tell me you got 38.95? Am I missing a zero?
Yeah, maybe on the 20,
Oh, I'm missing a zero, so then that's not moving.
I got this. We got 84.2.
Okay, let me try again. I lost a zero. 3, 0,
would be 19,
1, 8,
Also,
Yeah, so we get 84.
Oh, 5.
That's right. The first one.
84.51.
Should we do it to 84.5?
Alright, so let's answer the question.
I typed it.
I've been using, well, I guess that is T. So what does T stand for in this equation? Years after 1900. So when did the population get to be a million? About the middle of 1984. It was a million. All right, so let's pause there and go back through, walk through our steps. So the first thing we did, we had this equation they gave us. So we put in a million for the population. So now we're solving this equation. So we took this entire denominator and multiplied it over here. So it became a distributive problem. So we had a million times 1, and then a million times this 21 number equal to that. So now we took the million and subtracted it off. So we were left with this equal to what was left after we subtracted a million. Then we divided by this coefficient. So we had just e to the power equaled that fraction. This number divided by the coefficient. Then we ln both sides. This canceled, so my exponent equals the logarithm of that fraction. Then we had to get t by itself, so we divided both sides, so the logarithm of the fraction divided by this is what gave us our answer.
If you would have used, but that really makes sense, but if you would have used like log in this situation instead of natural log, would it have been,
You would have had the logarithm of the fraction divided by the logarithm.
Right. yeah, but just like right up there with like e to the whatever, would it have been like t times the log of
It would have been this log e, because the exponent would have been pulled off, and then you would have had log e.
Oh, okay, yes.
Yeah, right. So it's always going to be easier if there's an e already in the problem. It's always going to be easier to use ln, but you can always use log. always. Similarly, the problem we did before this, we LOG'd both sides, we could have LN. We would have gotten exactly the same answer. It doesn't matter what kind of logarithm you use.
Even though we already ln for the 3, 0, 1, that one, you just keep the ln?
Here?
Yeah.
Yeah, what are you gonna do with it? Is there an E over here?
Multiply it?
No, it's the logarithm of. So it's ln that fraction. You're taking the logarithm of it. It's just like logging, it's just like log. You got it?
Yeah.
Okay. All right, we already did that review part, so let's jump up and let's get to number 11. Number 12 is gonna be another one like this sort of maybe, I don't know. But let's look at number 11. You're gonna be doing lots of problems like this in the next few days, so don't panic if it's a little bit fuzzy right now. All right, graph the function and analyze it for domain, range, continuity, and all that. So domain, range, continuity, increasing, decreasing. So in other words, we're doing a function analysis of this. Symmetry, boundedness, asymptotes, extrema, and behavior. Okay. When we did these before, back, way back at the beginning, I think I told you I always like to do a graph, and this one does say sketch it anyway, graph the function anyway, but I think having a graph, even if it doesn't tell me, is always helpful. So, we know what the general shape of this is, right? What's its y-intercept? Well, it would be 0, 1, except we times it by 3, so now it's 0, 3. Have we shifted the picture at all to change its asymptote? The normal asymptote is the x-axis. Have we shifted it? No. So that's still gonna be my asymptote. And it's gonna look like this.
What would shift the asymptote?
We looked at that yesterday.
Yeah.
I messed up one of them, we had to fix it.
That move it up or down if it's plus one.
That would move it up or down.
Okay.
Yep.
Go
Now,
up.
this asymptote is horizontal, so the only way it's gonna move is up or down. Obviously, if you had a vertical asymptote, it would move left or right, but that would be something like, ln x has a vertical asymptote here. Remember, it looks like this. So if you did x plus 2, that would shift it. Okay, domain. What's the domain of this guy? All real. So we'll say negative infinity to infinity. What's the range? And should I include 0?
No.
Nope. 0 to infinity, no bracket there. That's gonna be a parentheses. Would you say this is continuous? Yep, on its entire domain. So I'm just gonna go ahead and say this is a continuous function. From negative infinity to positive infinity, I've never lifted my pencil one time. Is it increasing or decreasing? Increasing. On its entire domain, right? So it's increasing the whole way. Remember, we did look at functions, I'm thinking like of a parabola, that part of it was decreasing and part of it was increasing, but not this one. He's increasing the whole way. Does he have any symmetry?
No.
Does he have any, is he bounded at all?
Lower.
Lower, So I'll just say below at what? Y equals 0. He's got a 4. There's no ceiling. He's got a 4. Does he have any asymptotes?
Yes.
Yes. Y equals 0. Does he have any extrema? No. Don't manufacture critical values. Extrema, critical values. There's no peaks or valleys in this, right? So there aren't any of those. And then our end behavior, we're going to use the correct notation. We talked about this exact problem, I think, the other day, but we're going to do it again. What's my end behavior for this curve as I go to the right?
And positive infinity.
All the way to the right, that's shooting up, so that's going to be positive infinity. Now, you can put a plus in front of it if you want. Don't do this. This doesn't make any sense. If you want positive infinity, write positive infinity. Now, what as we go to the left?
0 from the top.
0 from the top. All right, everybody okay with that? Yep, Lucy?
So if we were to do this, it was like one of the problems on the homework, and it was for one of the equations that was about the logistic growth functions, those equations. When you're doing the bounding, would it be also bounded?
Absolutely. If it's a logistic function, it's going to have 2 asymptotes.
Okay, and the top bound would be the top asymptote.
Yep. All right, we're not going to get this one done, but let's at least get it sketched. All right, let's at least get it sketched so that we can come back from lunch and answer all of the questions. Okay. Where's the y-intercept? Remember how you find y-intercepts. Where's the y-intercept? I'm hearing 0, 3. How do you find a y-intercept? Let x be 0. That never changes. It doesn't matter what kind of equation it is. If you're on the y-axis, x has got to be 0. So if you put a 0 in here, that's 1. That's 2. That's 3. Uh-oh. 6 divided by 3 is not 3. That intercept is at 2. You guys lied to me. This is 2, right? If x is 0, that's 2. Plus 1 is 3. And 6 divided by 3 is 2. All right. What's our limit to growth? 6. Now, we talked about that the other day, yesterday maybe, or some days, we talked about that. But where that comes from is, I want you to think about letting x be really, really big. Like, talking about a limit to growth. Let x be really big, like 1,000,000. What happens when you raise e, which is 2.718, to the negative millionth power? What happens to it? It gets so small, it's effectively 0. So this becomes 0, and all you have left is 6 over 1, right? Now, flip that around, let x be really, really big negative, like negative 1,000,000. Well, then this becomes e to the millionth, which is a massive number. So the denominator is massive. 6 divided by massive is 0. So these are our asymptotes. And here is a picture of our curve. So when we get back from lunch, we'll analyze that. We'll show all the stuff. All right, we need to be back at 50, 50, in your seat.